Thank you so much, professors. Have been very impressive work, and you have shown multiple engineering strategies to for the graphene-based field effector transistor, and very wonderful work. And I saw several questions raised from the audience, and I will ask from my side because we have online like live channel to post your talk. Yeah, and one of the audience asked about the question is what are the main challenges for using graphene-based field effector transistor in complex biofluids such as like blood and saliva?
Well, I think this is what I try to explicitly explain in this talk. The
Mhm.
main challenge are these two things. It's the anti-fouling, which is present in all the sensors, but also this debye screening issue, because this high ionic strength would mean that you only have a debye length where you can measure up to not even 1 nanometer. So you have to think about surface chemistry strategies to overcome this. So one possibility to overcome this, I hope I convinced you in this talk using these copolymer approaches, this pyrene copolymer. This was quite a challenging and long project because what you need is you need a matrix which is anti-fouling, but also lets you integrate your bioreceptor at the same time, but is also thin enough that you can have diffusion of the analyte to the surface. Yeah. So it's a whole scenario for itself. Now, the work we did with non-covalent immobilization made us believe that we really think if this will ever make it to a commercial level device, everything has to be simple. Diazonium camphor is nice, but it's much more too complex probably for an industrial process. Pyrene chemistry is easy. You simply put it on the interface if you know the conditions. That was our idea to synthesize this pyrene copolymer ligand, which worked very nicely now on graphene. So with this type of things, open. You can add now any bioreceptor which you want on it, and you will have anti-fouling properties and overcome the bilength, the screening wave.
Yeah. Another question from the audience is about as you mentioned, the different engineered transistors. Among this, which one do you see as the most promising one for real-world application, like close to the clinical application?
Yeah, that's a good question, and there's always a debate. So what I showed you here, all these sensors are still liquid gated. That means we have the silver reference electrode in solution, but which has to be put to the sensor. That is not going to be the outline for a point of care device. What you will have to do is, you have to integrate the gate on the chip for itself. So there are several groups working on this. Even we are trying to do this now, but that will be the approach. And then what you have to do, then you have to do the chemistry, what we did just now, and see how far you get with this type of architecture. But it has to be a 2D architecture.
Yeah. Another question is about that you mentioned the MMP9 aptamer for wood fluid detection, and the question is any like a pre-treatment of the sample before like loading on the transistor for the detection, and do you need a like a microfluid device kind of to like for this sensing? Yeah.
Okay. For the moment, we don't use any fluid device because I do agree fluid device is extremely nice, especially in laboratories, but it puts costs into it. So if you could get avoided and get a good signal, it would be better. So in the case of the foot ulcers, how it works is the medical doctor makes a swab of the fluid there, and this has to be put then into the solution. So we put it into a PBS solution because you have to dissolve the biomarker, but then you simply use a droplet and can add it onto your sensor.
Okay. Yeah. And the another question from the audience is that when choosing bioreceptors, what do you think is the key factor to achieve good sensitivity and selectivity?
Um, as the transducer and the chemistry is important, the bioreceptor is essential as well. So it's a package, yeah?
Mhm.
I personally don't think antibodies are the bioreceptors adapted for this type of strategies because even so they're highly specific, they remain rather fragile. What you would have
Mhm.
like to have in a point of care, a person can leave it at home on the desk. You don't need a fridge where you stabilize bioreceptors. So I really think aptamers or nanobodies or even other bioreceptors like nanoclamps, yeah, recombinant constructs with higher stability in temperature and chemical stability that actually you can allow chemical modifications to direct link to your interest should be the future of this type of sensors.
Mhm. Okay, great. Yeah, actually, I have one question. Because you mentioned you have a different like aptamer modification for the signal production. I was wondering like it looks like a similar strategy in a like a surface plasma resonance. So how did you differentiate this sensing strategy to the SPR strategy and what would be the greatest advantage and the challenge in your FET strategy? Yeah.
I mean, you're completely right. gFETs and SPR are both what we call label-free techniques, no? In the SPR, you measure the change of the refractive index and or the optical density to get
Mhm.
to your sensor, while in the gFET, you measure a change of charge or current. I would say both of them have the advantages and disadvantages, yeah? Um, the SPR as it is, for sure, you will need a flow system. It's often you look at the kinetics on it. And as I just said, I think flow system is nice for laboratories, but for a point of care, probably it's not the device. So
Mhm.
probably some things have to be done here, but then it might not be SPR, it might be more localized surface plasmon resonance or creating ideas which will actually make it as a comparison to GFET.
Okay. Yeah. One last question from my end. In your last couple slides, you showed the future direction, kind of to replace the DNA aptamer to PNA aptamer, and your preliminary data showed that simply transferring the same sequence to a PNA structure, it will like still keep the high selectivity, right? That is quite amazing. I because previously I've done some work on the RNA aptamer and the DNA aptamer selection, and it is very sensitive to because the sensitivity relies on the secondary structure folding of or tertiary structure folding of the sequence. I was wondering, like, have you tried a different sequence directly transfer from DNA to PNA? Does do all of them work, or it is just kind of like you get lucky to have one work?
Well, it's quite challenging. So the reason we stick to CTNI, because
Mhm.
actually it worked.
Yeah.
There was work done, especially I mean, I'm not the PNA specialist, so it's my,
Mhm.
my colleague, Roberto Coriandini. He tried it on troponin. As far
Mhm.
as understood, it didn't work. Yeah.
Mhm.
So I would say for the moment, we are lucky. Um, it's an approach which should be tested,
Mhm.
especially what we will show in this paper is, if it gets complicated with PNA if there are too many amino
Yeah.
acids. So if you
Mhm.
manage it somehow to restrict it, to the length, then
Mhm.
the synthetic effort and the screening might be better. But I cannot tell why it works so well for the CTNI and why at the end it did not work for the troponin.
Yeah, and one last comment on that. I was wondering, like, because recently the artificial intelligence algorithm enabled the like de novo design of like protein binders, like for specific target detection. The de novo design binder with high affinity might be very useful in like for the surface modification in the graphene-based transistors, possibly offering a huge opportunities for a various target detection at a ultra high sensitivity and precision, right?
You're completely right. I mean, all these tools, which are definitely important also for biologists, will help us
Hmm.
a lot to screen faster and also
Yeah.
get information of where the binding is and where not binding is happening to construct the structure. So I think, yeah, in the years to come, you will see much less experimental effort, but artificial
Hmm.
intelligence and modelization efforts.
Yeah. All right. Thank you. So, yeah, I've asked all the questions from my end, and now I will hand the microphone to Jenny.
Thank you, Professor Xu, and thank you, Professor Sabine, for your valuable presentations. And any question from our audience? Okay, since there's no questions, I will give the closing talk. Thank you everyone once again for joining us today, and please feel free to reach out if you have any questions about our journal, and also would like to learn more about our journals. And we look forward to your continued attention for our journal. Have a nice day. Hope
All
to
right.
see you
Thank you.
soon. Thank
Mhm.
you.
Thank
Bye.
you.
Bye.
Bye.
Bye.